So today let's take a look at the Neo Geo AES consoles, and I'm going to focus on how to properly fix the RGB inputs. So if we Google for fixing Neo Geo AES RGB outputs, we get a couple of articles. But the problem is there's so many revisions of Neo Geo, and not one of these articles really correctly addresses it. So if we just take a look, and if we were to Google for Neo Geo RGB, you'll get this mod first. This, I believe, is probably one of the earliest ones. That's why it shows up first. And it does a good job of showing and explaining. You've got blue, green, and red inputs. You've got some AC coupling caps. And on this specific revision of board, they remove these components. And what they're effectively doing is disconnecting the output from the LSPC chip, going to the CXA amp, which then completely disables composite, and wiring straight from the LSPC pins to the AV out. I wouldn't recommend doing this because this will load up the LSPC chip, and it might not be capable of syncing that current, and you also lose composite for no reason. It at least uses 75 ohm resistors, which is correct, but again, the output from this might not be correct, as these come from the LSPC through some D-type flip-flops and then out to the AV port. Things can change and vary there, so there's no real measurement, as well as this is only for one revision of board. So it does an okay job and it'll work. The next most popular one will be this retro RGB one. This does a good job of showing nice visuals of what the solution is. Again, it disables composite video because it's based on the same mod. But this is a much worse guide because it simply says, unscrew stuff, solder things in, and away you go. There's no explanation as to why you're doing really what you're doing. They've even resorted to just labeling caps 1, 2, 3 and resistors 4, 5, 6. And I've seen so many boards come in our shop for repair where people have clearly attempted to do this mod on a totally different revision and just found resistors in a near proximity. And that's simply because they don't understand why they're doing what they're doing. There's no explanation as to what these pins are, why we're doing it. It's just very vague. So I thought I'd show you how I fix the Neo Geo AESs. And yes, again, this mod works, and there's some outputs showing it clearly works, and the voltage levels are right. So I'm not saying the guide's complete trash, I'm just saying it doesn't really teach the consumer of this mod what's actually going on and how to fix their revision of board. Like, why are we doing this? Where's the problem? What's the solution? How do we scope for the problem first? So what I'll do is use this board. This is one of the first revision boards we have, and I will talk you through this circuit of showing you the problem and then showing you the solution and watching through a scope exactly what happens. As with everything I do, I provide a full write-up and documentation that you guys can follow. So this is no different with the Neo Geo. If you want to go ahead and read all this in your own time, this will give you all the technical details you need, and this video will supplement that. So in short, I'm reiterating kind of what I've said here, that no guide really explains why you're doing what you're doing, or even talks about how the RGB is generated. So I've done a little schematic here, which is just screenshots of the original schematic and pages pasted together. And what happens is the LSPC chip here, which is this chip here, and you can easily identify it by the fact it says LSPC. This will normally be around this area, sometimes over here. But all you need to look for is the text LSPC. Then you know that you've got that chip. The RGB is generated from there through bits coming in. They go to two flip-flops, which are 74 LS273s. And on this particular board, they are these here. They're normally identified by either you see the traces coming out, going up and heading towards here, or you'll see a ton of resistors, which is the resistor ladder next. And obviously the chips themselves will say LS273. So there's various giveaways. And I believe they are the only LS273s on the whole board, so you should be able to find them fairly easy. What happens is the red, green and blue bits go into these flip-flops, they latch, and then the outputs are sent through a resistor ladder, so all these resistors here, that finally generate red, green and blue outputs as single analog voltages. So red, green and blue comes out of this, goes to these, latches up during clocks so they stay valid, outputs to all these resistor ladders, they all collapse down. They head back down here in this case to a voltage divider network, which is then this voltage divider network here. And that's easily identified by the fact that it's got 6.8K and 2.2K written on the silk screen. So you've got 1 ladder, 2 ladder, 3 ladder. And you'd expect them, considering the resistor ladders are up here, that they would be up here somewhere, but they're not. They come all the way back down and go to here. So what happens is the red, green and blue signals come out as analog here. They're too high voltage for full width and spec, and they go through this little resistor divider here. They have AC coupling before they go into the actual video encoder, which is the CXA chip, which is here, and it'll be always by the AV port, and it's labeled CXA1145. So red, green and blue out, digital out, through resistor ladders to analog, through voltage dividers to apparently the correct level, which is the problem that it's wrong, through then the CXA encoder chip, which red, green and blue come in, and then finally come out, go through AC coupling and a resistor that should be 75 ohm and is incorrectly 68, and then out the AV port. So that's a general overview of what happens, where the colours come from and where they go to. And the problem is, if we turn on, and you'll see here, an easy way to detect this is leave a game out. I'll just bring this in. I will get a capture card, I just don't have one on me at the minute for capturing RGB. And if we turn on Window Game in, you can see the BIOS loads and you have blue. But the thing is, this blue is meant to be pure blue. And this menu on the OSSC converter is also pure blue. So you can see this background should be perfectly the same colour as this menu. So visually you can tell this is not good. You can also see here, see the lighter blue fading to darker blue here. This is because of field tilt and droop due to these capacitors being the wrong size and the fact that it's AC coupled and we don't really need to be anyway. So that's the visual issue we have right now. But instead of just telling you there's a problem and let's slap some resistors on, you can see I've got the oscilloscope hooked up. We've got the C-Sync pin and the blue pin hooked up to 2 channels of the oscilloscope. And just before we jump into that, let's take a look at what we are expecting to see. So the output voltage problem is effectively that the IRE standard for RGB, which the red, green and blue are luminance levels, they should be 700 millivolts when your AV port is actually terminated, so connected to a receiver like the TV, because that adds a 75 ohm resistor. So if you take a look at this, inside of a TV or the OSSC or similar, you have a 75 ohm resistor to ground on all of them. Sometimes you have AC coupling, sometimes you have DC restoration, sometimes it's just a transistor. But the common thing is you're effectively forming a voltage divider with a 75 ohm resistor to ground. And a voltage divider is like this. So we have the 75 ohm resistor in the TV or the receiver. And this R1 here is your resistor on the board here, the 65 ohm, which is effectively these 68 ohm resistors here going to the output of the AV port. They come after the CXA chip. So these being slightly less than 75 ohm will actually increase the voltage, which is probably a sign that SNK knew the voltage was too low and slightly compensated with a resistor, just not enough. So back to what I was saying, what is it that we're expecting to see? So the red, green and blue levels should be 700 millivolts roughly, and the sync pin is similar to the sync level, so it should be 300 millivolts. So we're expecting 0.7 volts and 0.3 volts on the blue and C-Sync respectively. So let's take a look at the scope and see what we actually have. So you can see here I am capturing the C-Sync pin on the blue channel and the blue on the red channel. If you watched the previous video on using an oscilloscope, I'll show you how to set up these triggers and capture these exact voltages. But you can see straight away a problem here. So see this droop here? You have a slow rise, then a high blue, and then a trailing droop down to low. That is what's visually causing this bright blue fading to dark blue. That's literally that droop here. So the high blue fading down to dark. That's the visual representation of it here. So that's problem 1 you can see on an oscilloscope, and then when we fixed, we can confirm it's gone. The other issue is, let's just measure the C-Sync level, which should be 300 millivolts. And you can see it's 338 millivolts. So it's not far off, that's adequate. Probably ever so slightly high, and there's also a slight droop even in that, so we should bypass that as well. And there's even a slight droop on the C-Sync as well. But the C-Sync won't be as big of an issue because it's not color related, it's purely timing related. So the C-Sync's okay for now. The bigger problem is going to be the red, green and blue channels. So if we use, say, this flat piece here to measure the height of the pure blue, this should be 700 millivolts. And we're getting 482 millivolts, so significantly lower than it should be. So the problem comes from the fact that the CXA chip is outputting here, and people look at this and go, the 68 ohms, they should be 75. Well, in a voltage divider network, increasing these to 75 ohms will make it worse. You'll have a lower voltage output. So the output isn't the problem. We could change these to 75 ohms, but it won't change much. 68's fine for now. These capacitors are causing droop, which we'll fix after. But how do we fix this voltage level correctly? So we'll see here we have the input side of the network, the voltage dividers, and this comes out of the LSPC, goes through this voltage divider, lowering the voltage. So you can see it goes through these input resistors into the CXA chip and then out. If we look at the video encoder, I explain in here all the inputs, so you can see the red, green and blue after that voltage divider come in here and then go out. The amplification of the CXA chip as well, from observations, seems to be around 40%. So if we send 0.66 volts in, we're going to get 0.93 volts out. So we get a rough 40% increase in voltage. So the solution to correctly fix this low voltage is not to alter the output stage. So there is an output stage fix, which is what most of them tend to do, or bypassing the chip altogether, which is also not really a good solution. There's no point to bypass it. What we want to do is simply alter this resistor divider network. So 6.8 and 2.2, if we're lazy and we just go to a voltage divider calculator and we put in, say, well, in fact, let's just measure what the output voltage is first. So if I was to just take the second probe and probe the voltage in on the blue pin, so we've got red, green, blue. You can see now on the red channel, this is the blue, the voltage coming in to the CXA is about 0.66 volts. Coming out of the CXA is about 0.9394 volts. So you can see the voltage in is 0.6, the voltage out is 0.9, and then the final voltage from that forms this massively under 0.48 volts. So the principle should hold true that if we increase the voltage coming into here, it will increase the voltage coming out the other side. And to do that, we can change the voltage divider. So let's just do some calcs. We have a source voltage going in at the minute of 0.66 volts. We have 6,800 ohms in one, 2,200 in another, and it calculates out. So if we just pump in the values of, say, 1 volt with the resistors, because we only really care about the proportion, and we put 6.8k in and 2.2k on the second resistor, forming the voltage divider that we actually have, you get 0.244. This number is irrelevant. We want to figure out how much we want to increase by. So we wanted 700 millivolts on the output, but we actually got 460 roughly. So we need about a 1.5 times increase in voltage. So if we just change this to a voltage where this comes out at roughly 1 volt for nice and easy calculations, you'll see what I'm going to do in a second. So about 4.15 there. Right, so we have roughly a 1 here, and this wants to turn into 1.5. So the voltages don't matter, it's just the mathematical division. So if we were to lower the 6,800 to say 5,000, you get 1.25, so we need to go less. Let's go 4,000, nearly there. Let's try 3,000. That's too much. 3,400, a little bit too much. 3,700. So you want roughly a 3.7k resistor instead of a 6.8k. So instead of removing the resistor, let's just do a voltage parallel calculator instead. So now we're going to stack on top. So we have one resistor that's existing already there, 6,800. And we want to stack something. So let's put 6,800 as well. We're trying to get this to be about 3.8k. So 6.8 is a bit too much. Or a bit too little rather. Let's try 7, 8k, 9k. So between 8 and 9k roughly, if we were to stack a resistor in parallel with this one, so effectively if we were to solder a resistor on top of each of these 6.8ks, 9k, it would form ultimately the expected voltage increase of about 50%. This should fix the voltage level issue. And here we have some 8.2k resistors, so that's close enough, I reckon. We'll turn the console off. Let's just solder one to the blue channel. And to find out which one of these is blue, we know from the wiki, if we go to the video encoder, scroll down, you can see the blue in is 4 pins over, so 1, 2, 3, 4. So we can use an oscilloscope to probe pin 1, 2, 3, 4, track it back, and it will go to this resistor here. I can actually see the trace going from here, through this cap, out this way, up into pin 4. So it'll firstly go to one of these 3 caps, so there'll be red, green and blue, and those caps will ball out to red, green and blue here, and the other side of those caps will then go to these resistors. So you just got to use your multimeter and follow the schematic. So in this case, this one is blue. And this will vary on revisions of board, so don't just go based on location, do use the multimeter. And what we're doing now is reducing this 6.8k ultimately to about a 3.8K. You could just take out the resistor and swap it with an actual resistor of the size that you need when you've done the calculation, but I'm just doing a parallel one so I don't have to remove existing components. So with that on now, let's get the screen in here and let's turn on. And you can see now the blue is, I would say, probably correct. We've got a slight bit of field droop here where it fades, but I think that's nearly, it should be identical to the background here. So it maybe looks a bit under, but the solution is to obviously look at the oscilloscope. So if we take a look at the oscilloscope and we put the probe back on the blue output, we can now measure what voltage we get. And this wants to be 0.7. You can see 0.725, so that's perfect. So that is now a perfect voltage level. The problem we will have remaining is that you have field droop. So it starts off perfectly the same color, fully saturated, and then it's fading down to darker due to this capacitor issue. So on the subject of the capacitors, if you're interested, if you read our clean RGB SCART cables right up, I will be mostly focusing on pure DC coupled RGB cables, not these AC coupled that everybody else does. The AC coupling is a real legacy way of protecting really old CRTs that had pure transistor-based drivers on the input stage. This is incredibly rare and almost non-existent to this day. So if you're going to use really old CRTs and you're worried, I'd buy an AC coupled cable and not AC coupled a console. But we're going to be selling DC coupled cables as the primary cable, and our mods for RGB like this are going to be DC. There's no need for AC. So if you want to read up about it, don't listen to me, listen to Analog. They know much more than I do. And read up about the whole issue with legacy AC coupled video output and how it causes this field tilt and droop that you've just seen. And also why it's completely pointless doing AC coupling. There's absolutely no real need to do AC coupling. So my choice is we're going to DC couple this Neo Geo. So what that means is you could remove all these caps, but instead you could also just bypass them. So if we take a look further down, you will see that we could either replace the caps with much larger caps on the output stage, and this is the issue we're seeing, this fade between visuals. So what the proposed solution for the droop is we're simply going to remove these caps here on the RGB lines. You can remove it on the sync line as well. You could remove it on the composite and you'll probably be fine too. And what we're trying to fix is these big droops here on the voltage levels. So to do that, you can find the caps nice and easy. AV port, 68 or 75 ohm resistors, going to 100 or 470 microfarad caps, and then they go to the CXA. So these are the ones we want. I turn the console off, flip over, and these are the bottom of the caps. Here's the red, green, and blue pins and the sync pin. So I'm going to leave the 10 microfarad one unbridged, but I'm going to bridge the red, green, and blue pins, the sync pin, and the composite pin. So we're going to purely DC couple this entire console. This also means we don't have to remove a single component from this board, and this mod is completely reversible in seconds. You just take off a couple of resistors and a couple of shorts. So with that done that side, let me just fix the red and green channels as well. So this is fully done. And that's those resistors on there. I'll tidy them up and probably solder them underneath after the video, but that's all the parts on. So now let's take a look, turn on, and we can see there, we now have absolutely no field droop whatsoever, a perfectly flat line, and 730 millivolts. So within 30 millivolts of absolute perfect. And that's probably going to be much more accurate when we're close in. Yep, so we're about 30 millivolts over, which again, if you want to go perfect, you can just slightly increase that 8.2K resistor, maybe put another 200 ohm or 100 ohm resistor in series with that. Let's just take a look at what that now looks like on the actual video. And you can see they're absolutely flawless. So the pure on-screen menu of the OSSC is exactly the same color as the Neo Geo output. There's absolutely no difference, and you cannot see a blue border at all, no matter where you look. So that is perfectly balanced. Let's chuck in a game. And let's just take a look at what this now looks like with a perfectly balanced RGB output. So the white's pure white on here. I can tell you now that's as bright as the white gets on this monitor. And that's super bright. So we should have shown a before and after, before doing this mod, but I have actually taken photos, so I can show you those in a moment. But you can see that's now perfectly clean. There's no clock interference, there's no noise. This is absolutely perfect RGB output and couldn't really look any better. So that's this mod done now. We have pure RGB, the perfect spec. We haven't had to remove any components, and we've still maintained composite output. So this has got every output going and can be easily reversed. Just remember your revision of Neo Geo will be different, but just follow the principle that the LSPC generates the RGB. Look for the 74 LS273s, go through the resistor ladder. They should make their way to a set of 6.8K and 2.2K resistor dividers, and that's the point where you want to then adjust your voltage. You could swap these out for potentiometers, like a 10K potentiometer, and just turn it with a screwdriver, watching for the perfect blue output to set your level to 700 millivolts. And that's probably the quickest way of doing that, and I just recommend always bridging your caps. That should then be the easiest RGB mod that works across every single revision of Neo Geo. If you do need more assistance on this, just jump on discord.gg/retro6 and you can jump into our community. We've got over 5,000 members and growing rapidly, and I'm there every single day helping everyone for free. So I hope you enjoyed this one, guys. That's it for now, and I'll catch you in the next.